Thank you, Arancha, and thank you to all who came on a Friday morning. So this talk is about programmable privacy on the application and protocol layers, and I want to start with just the motivation for this talk, which is sandwich attacks. So I'm sure everyone here is familiar with sandwich attacks. Sandwich attacks are fundamentally caused by the presence of privileged actors who have full visibility into every transaction and are free to reorder them or insert and delete transactions. So how this can be used to harm the user is through a sandwich attack, whereby the operator of an order book inserts a trait in the other direction right before executing the user's trait and causes the user's trait to execute at a worse price. And then afterwards, the operator inserts yet another order that arbitrages this trait back. So why this is concerning is because users are getting worse execution and privileged actors are benefiting from their users. So the naive solution to sandwich attacks is this sort of brute force kind of privacy, which is the encrypted mempool. And this is what is done in osmosis. So every transaction in the osmosis mempool is encrypted. And what this means for the block creator now is that there's no point of reordering transactions because they all look like random ciphertexts. Now, a few problems with this naive solution. The first one is that it's not efficient. So while it's true that the user is protected from sandwich attacks, there's also no opportunity for the user to benefit from a good ordering of their transaction. And secondly, this random ordering actually privileges the transactions that are commutative. So transactions that do not depend on any ordering will still execute perfectly fine, whereas transactions that rely on coming immediately after another transaction might revert. So some of these problems could be solved by lighting up certain areas of the transaction or like expressing their dependencies as covenants. But yeah, generally this raises the question of how can we preserve trait privacy while also achieving trait efficiency? And a more general way to ask it is how do we preserve intent privacy while being able to match users' intents efficiently? So at the core of it, programmable privacy is interesting because it increases users' welfare. And yeah, this work today is part of a systematization of knowledge paper that I'm co-authoring with a few collaborators. And what we're aiming to do is formalize sort of the computational frameworks used in these programmable privacy solutions, and also examine like the information leakage and the security assumptions that go behind each of these solutions. So what we're gonna do is we're gonna examine all of these solutions using just one application, which is the limit order auction. And we're gonna see how the limit order auction is implemented in each of these different solutions. So I'm sure you guys are also familiar with the limit order auction. So what a limit order is a commitment to sell a certain amount of an asset in exchange for a certain amount of another asset. So there are many variants of limit orders. So in an order book, the user specifies both the amount and the price that they want. So the price over here is going to be 10B over 5A. So I will only sell asset A if I can get 10 units of asset B or more. That's the limit price. Whereas in an automated market maker, the user does not specify the price. The price is specified algorithmically as a function of the liquidity available. And yeah, so the user can specify a slippage. So they will trade within some delta of the public price, but if the price slips beyond that delta, then they won't execute the trade. So in both of these cases, programmable privacy aims to conceal the user's trading strategy. So there you'll see many variants of designs, some of which only care about pre-execution privacy, and some of which care about long-term privacy, even after the trade is executed. And we'll go into basically what exactly is concealed and how this affects user privacy, user welfare. So maybe one way to understand order books and AMMs is through CowSwap. CowSwap actually uses both AMMs and order books. So what they do is they batch all the orders coming in, and then they share liquidity for all the orders with the same limit price. So they match the orders using both an order book and an AMM. So yeah, definitely these two designs can interact. The second part of the intro section is going into the cryptographic primitives that are used in these privacy-preserving constructions. And this will be just a high-level overview. So we're not going to understand the math of it, but we will understand the API. So I think of the cryptographic primitives in sort of two classes. The first is private verification, and the second is private computation. So private verification is pretty much zero-knowledge proofs. Or it's also this proof-carrying data that you might have heard of from this, like in your ZooPass. Like your frog is an example of private verification. So basically, all the computation is done client-side. All the computation is done by a single prover who knows the entire witness. And what the prover generates is a short statement that is publicly verifiable and that attests to certain features, certain properties of their original witness. So the key here is that the verifier cannot do any further computation or manipulation of that witness. Instead, they can only verify yes or no on certain desired attributes of this witness. Whereas private computation is basically encryption. So it is a structure-preserving way to represent your private witness. And why you want to do this is because the bulk of the computation is happening server-side. So basically, all you're doing client-side is encrypting your data, and you're leaving the server to do the computation blindly on your ciphertext. So this private computation is often done in the threshold setting, meaning that instead of trusting a single server, we encrypt our data to some threshold of servers. But in the case of trusted hardware, then it's sufficient to use a single server. So yeah, this is also This comparison also shows us like what are the trust assumptions and what are the threat models that we have. And based on what's acceptable for your application, you would pick one of these. By which I mean you would pick between either the threshold or hardware private computation. So for most of these collaborative privacy applications, we'll see that private verification is not sufficient. And in fact, we need the server to be able to do further computations over multiple private inputs. And in reality, a lot of these cryptographic primitives are stacked. And for example, zero-knowledge proofs are used as a primitive in any system that uses FHE. And they're used as a proof that the ciphertext was the result of of following the proper encryption procedure. Another example is zero-knowledge proofs being used to make an MPC publicly verifiable. So besides performing the joint computation, the parties in the MPC also produce a zero-knowledge proof attesting to the validity of that of the computation. So basically, zero-knowledge proofs help us to audit these private computation methods. It helps us to check the well formation of messages that are encrypted, and it helps us to check that parties in an MPC followed the correct procedure. Another example is, I said just now that if you're using TEEs, then a single server is enough, but actually TEEs can be used as a defense in depth. So in an MPC, you could put each share of the key in a TEE. And so this gives an additional defense for key security. So that concludes our introductory session. I hope we're sufficiently motivated and we have a good understanding of what tools we have. And we can now go into some of the constructions. So today we're going to cover 2 order book constructions and 2 AMM constructions. And I didn't have time to put it into my slides, but I'll talk about another order book construction in between those. So the framework that we're going to be using is basically 3 phases of computation. In the first phase, it's when a single user pre-authorizes some intent, and they authorize a set of actions that can be executed by a set of parties. So this sounds abstract right now, but for example, a limit order is an intent. So they authorize the spending of a certain number of assets if in exchange they get a certain number of assets or more. Phase 2 is when multiple users' intents are matched. And this is the interesting phase, because this is when you see these solutions start to differ in terms of the privacy guarantees that they offer. And this is when solutions using private computation can actually preserve user privacy. And phase 3 is when these intents are executed, and this is done globally. So by the time we reach phase 3, we shouldn't be working on private information anymore, and we should be able to broadcast messages to the whole network and update the network state. So the first example is Zaxi, and I'm not sure how many people here are familiar with Zaxi. So basically, Zaxi is a protocol that allows you to specify arbitrary programs that you want to verify in zero knowledge. So if Zcash is a protocol for payments in zero knowledge, Zaxi is a protocol for arbitrary programs in zero knowledge. And how you express your programs is through birth and death predicates. So a birth predicate is something that you must satisfy in order to create a node, and a death predicate you must satisfy to consume a node. So how do we build, and a transaction consists of a balanced set of records for which all their birth and death predicates are fulfilled. So how we would implement a swap in Zaxi is that we consider one of the inputs as the take order and one of the inputs as a make order. And we are going to encode the terms of the trade in the birth and death predicates. So in Zaxi, this is called the exchange or cancel predicate. Exchange meaning the success case in which the outputs are actually just the swapped version of the inputs, and cancel meaning the failure case in which the outputs, in which there was no successful match and there should have been no change in ownership of the assets. So yeah, I'm not gonna go into detail, but that's the high level how Zaxi works. So in phase one, both the maker and the taker spend the nodes that they're intending to trade. So they create these output records. And these output records are gated by death predicates that encode the conditions of the trade. So in order to consume these records, they must have access to basically like an exact match. So now in Zaxi, there are several variants of order book you could implement. And the privacy preserving variant is the closed book exchange. So basically, in this exchange, you would expose the information required to consume your order to the order book operator. And it's private in that sense from everyone except the order book operator. So the order book operator has access. They have a viewing key, and they can basically look at the information behind each of these records. And if they see two that match, then they'll consume those records and create output nodes that represent the other side of the trade. So together, these form a balanced transaction, and the operator submits the transaction to the global network along with a proof that the birth and death predicates have been fulfilled. So yeah, in this case, the guarantees are privacy from everyone except the operator. So to a third-party observer, they'll see some records being consumed and some records being created, but they have no idea the asset IDs and the values behind those records. And furthermore, the operator cannot steal these records because these records are gated by the death predicates. So the only way to consume these records is to actually fulfill the trade or cancel, meaning return them to their original owner. So yeah, there's no privacy from the order book operator, and the question here is this okay? Is this still interesting in the context of programmable privacy? So we can think of this sort of as a dark pool in TradFi, where yeah, the trust assumption is the same. You're trusting that it's in the operator's interest to not share your orders with the wider mempool, and your main goal is to conceal your order from the other people trading on the order books. So, for example, if you're a whale and you're trying to dump a huge amount of assets, you don't want this to be visible. Like, you don't want the order to just be lying there and be slowly devalued, such that by the time you make your trade, it's like worth a lot less. So this is what we just discussed, how you would implement a closed order book in Zaxi. There's other variants, like, for example, an intent-based order book. So they mentioned in their paper, you could broadcast simply the direction of your trade, and we assume an out-of-band communication channel where interested counterparties can coordinate with you on your trade. So a similar but more recent implementation of the closed order book is in Taiga. And I think of Taiga sort of as a rephrasing of the Zaxi protocol that puts something called the intent front and center. So how you would implement a swap in Taiga is, firstly, the maker, as before, they would spend the note that they're intending to swap, and they would output an intent note that encodes the terms of the swap. And the taker does this similar thing. And then, yeah, these intents are sent once again to a solver who matches intents, who consumes the intents and outputs the corresponding take and make that satisfy those intents. So now the partial transaction consists of these six. So now the balance transaction consists of these 3 partial transactions. And once again, the order book operator sends the balance transaction to the network, along with the proofs that they satisfied the predicates in each of these records. So, yeah, how I understand Taiga is that it is sort of a reinterpretation of Zaxi to allow the simple composition of these partial transactions. And if you want to look more into the details of how Taiga how Taiga differentiates itself from Zaxi, they actually wrote a blog post about this called Zaxi versus Taiga. Yeah, there's some details in there, such as Zaxi always requires proof of ownership for a certain public key, whereas Taiga sort of abstracts over this and yeah, does not always require proof of ownership, but in Taiga we're allowed to gate the consumption of a record on any predicate. So yeah, these are pretty low-level implementation details, but how I understand Taiga is just a more convenient rephrasing of Zaxi. So oh yeah, and here's what we discussed written out in text. So I wanted to quickly mention a third order book construction. It's called Renegade Phi. And basically what they do is they do this matching on-chain. So they have this sort of MPC threshold that is performing these matches. And in that case, you're not trusting a single solver anymore. You're trusting the MPC nodes in the Renegade network. And yeah, this is basically weakening your trust assumption. So I don't have a slide for that, but it's a very similar idea, except with better trust assumptions. So the next two protocols are implementing AMMs. And the first one is secret network. So secret network, each node in the secret network is a trusted execution enclave. And it holds a consensus seed. And users encrypt every transaction to this consensus seed. So now in secret network and in an AMM, the prices are public, and so the user can publicly determine the optimal route for their trade. They encrypt their trade and route to the secret network consensus seed, and inside the TEE, this is decrypted and used to update the state. And the state is re-encrypted and output. So a few things to note about secret swap on secret network is, firstly, the identity of the sender is revealed. The trade is not revealed, but the identity of the sender is. And secondly, I tried out secret swap, and I realized while looking for my transaction that each block in secret network has basically 0 transactions. My block had 1 transaction. So why this is worrying is because by observing the change in the public prices, it is very clear like what exactly my transaction did. And because my identity is revealed, then yeah, I got no privacy out of a trade. So the thing to note here is that trade privacy in an AMM comes from the size of your batch. And if there were other transactions in my block, then I could have some plausible deniability, and like I could say, oh, that wasn't my trade, that was this other transaction. And yeah, this idea of batch swaps is integrated into Penumbra at the very core of their protocol. So on Penumbra, what the users do is, once again, they encrypt their swaps to, this time, some threshold key in the Penumbra network. And they encrypt it such that the ciphertext can be homomorphically added up. So any node can add up, anybody can add up these ciphertexts homomorphically, but only a quorum of the Penumbra threshold working together can decrypt the batch amount. And so this decrypted batch swap is made public and is traded publicly on the AMM. So once again, all the prices on the AMM are public, and this batch swap is also public. And later on, users can privately claim their share of the swap outcome by proving knowledge of some, by proving the knowledge of some input to the original swap. So once again, the privacy here comes from the size of the batch. If my batch has only one swap, then I get no privacy from it. And furthermore, the trust assumption here is that we won't have a quorum of validators coming together to decrypt individual swaps. So yeah, it's just different trust assumptions. But as in the case of secret swap, privacy depends on the size of the batch. So I think I'm almost at time. I did want to leave off with a few thoughts and a few open questions. So yeah, we're in the process of writing this SOK, and what we've realized from surveying these implementations is that there's a lot of information leakage that is not inherent to the protocol, but is a result of possibly the application designer or the user's interaction with the application. So the point of this SOK is to formalize these models for information leakage, and to be able to assess any programmable privacy protocol with relation to these measures. So yeah, and I think, yeah, it's also been interesting to ask basically what is enough, how much privacy is enough to preserve user welfare. So in some cases, is anonymity enough? In some cases, is pre-trade privacy enough? And in which cases do we need like long-term privacy, even after the trade execution? Yeah, so I think that's almost all my time. I think I'm over time. So thank you very much. That's my talk. Yeah.